All right, well, welcome everyone. I am JJ. Let's tackle an example problem. We have our plate shown here, has a mass of 25 kilograms. It's supported in our horizontal position in the XY plane here by two hinges, hinge A and B, and then a thin link here, CD. The hinges are properly aligned, which is just telling us they aren't resisting moment in here, only forces. And hinge B is resisting any force in the x direction. Really, we're just saying AX equals 0. That's a given for us. Otherwise, we'd have 3 unknowns at A, 3 at B, and a force in our thin link. 7 unknowns. We only have 6 equilibrium equations. It'd be mathematically unsolvable for us. So we're just forcing AX. We're assuming it's 0, so we can solve this problem. So let's find our support reactions. So I've come in and I've drawn in already kind of the general layout of our object that we can fill in. Otherwise, this takes me forever to redraw. It's just a bad use of time. So let's come in and label our unknowns in here. So I know at A, I have a support, a hinge. Hinges resist force in the X, Y, and Z direction, except we were told AX is 0. So I just need an AY, and I'm going to assume this goes in the positive direction. AY. I need an AZ. AZ. And again, AX we're assuming is 0, so I'm just leaving it off. At B, I will put in BX, BY, BZ in here. So BX, we're just going to assume in the positive direction, BX. I always label in my pictures the positive ends of my axes, so we know which end is positive in here. BX, BY, and going straight up, BZ. We also have a thin link that goes from C to D. Thin links, kind of like cables, when we dealt with 2D, where we said they could be in tension, except the thin link could also be in compression. So I could either guess that this goes from C up to D, or from D down to C. It really doesn't matter. The math is going to let us know if we made the correct assumption or not. I'm going to guess that this points from C and goes in a straight line up to point D, or that is CD, the force in thin link CD. The last thing that I need is at G, the center of a rectangle. I'll put in the weight for this. And we put the center because the center of a rectangle is in the dead center. So our center of gravity should be in the middle. So I'll show this coming straight down. And let's find what that is before we move on for everything. We know that's a weight. I was given a mass. My very first step is just going to be, let's convert that weight or that mass to a weight. Our weight should be our mass, 25, times gravity, 9.81. Or this is 245.3 newtons. So we'll fill that into our free body diagram. 245.3 newtons. And that does fill out our free body diagram. We have all of our forces, all of our distances labeled on here. We can work with that and keep moving forward. So if I'm dealing with this in 3D, we could either try to come in and do just that general force times distance approach, or we could try to set up a whole bunch of cross product matrices. They're going to get us to the same point. I think that the cross product matrix is a little bit easier. It's more tedious. It takes me a little bit longer to get through, but it's my more surefire way to get somewhere. So I'm going to tackle this one using the cross product for everything. So if I'm doing that, I need to say, well, my first step, I need force vectors. Remember, if we're dealing with the cross product, we're really saying our moment from a force is a position vector crossed with a force vector. So for us, we can come in and work with this. Our moment vectors, about any point we want to take a look at, have to entirely add up to 0. So our moment vectors about any given point is our position vector, or the moment arm vector that goes from this point to a force vector crossed with a force vector. I'm going to need position vectors and force vectors. This will give me my first step. So let's do step 1. Let's get each force as a Cartesian vector. That way we have our F's in there. Express each force as a Cartesian vector. So let's come and do that. Basically, anywhere that I have forces in here, I need to get a Cartesian vector. So I have forces at A, so let's get an A vector. My A vector is just going to be, well, I have 0i, there's no AX, so 0i. In the Y direction, I have AY, so plus AYJ. In the Z direction, I have AZ, plus AZK. I have unknowns in there. That's okay. That's eventually what I'm going to end up solving for. So that's really all I can do with that one. So we can move on and do B. B is going to look really, really similar to us. My B vector, all I'm adding in is a BX on this, is BX in the I direction. Plus BY in our J direction. Plus BZ in our K direction. And we can put in newtons, would be our units on all of those. Newtons and newtons, matching our force for our weight. Let's get our weight as a Cartesian vector in here then. Our weight vector, W, should be, well, weight's going straight down. There's no I or J component on this. So 0I plus 0J. Our weight goes down, so that's a negative K, minus 245.3 K newtons. And our last one that I need to come in and get is FCD, my force vector that goes from C to D. Well, this one I'm going to have to use position vectors. I can get coordinates to find position vectors, find their magnitudes. I can work with those to make a unit vector. But really, my equation here is my force vector is the magnitude of FCD times my position vector, R is position vector, that goes from point C to point D, divided by the magnitude of RCD. So I'm going to need to get a couple pieces in here. But that FCD, that's the unknown I'm actually going to solve for. So I need to fill in the position vector and its magnitude. Remember, we read this. This is a position vector that goes from C, the first letter in there, to D, the second letter. D is the tip of that. C is the tail of that. So if I'm trying to find RCD, I should do tip minus tail for this. Let's just fill that in one go for everything in here. My FCD should be my unknown FCD times my position vector. In our x direction, I am on that YZ plane for both of these. So the tip is at 0, the tail is at 0 in the x direction. So 0, I. In our y direction, the tip here is at positive 0.65. The tail C is at 0. So 0.65 minus 0 will get us plus 0.65 J. In our K, the tip is at 0. The tail is at, we've gone down, 0.95. 0 minus a negative 0.95 will be plus 0.95 K. That's my position vector, RCD. I'm dividing through by the magnitude. The square root of 0.65 squared plus 0.95 squared. If that step feels hard or confusing to us, we should probably take a look back at previous videos. I think the 3D vector one would cover that. We could also probably take a look at 2D particle equilibrium, would have touched base on that as well. Same thing, 2D moments probably use that, or 3D moments, probably use that some. But review some of our earlier material. We'll get you there. I'll try to link a video in there to help out with that. But we can say this is our next piece. We are in newtons for that. Which if we actually do the math in here, rather than using our square root, we don't want to carry that through all of our work. We're going to end up getting that this is our unknown FCD times our I component is 0, so it's just 0I. Plus our J component would be plus 0.056, 0.5647 FCD J. And then our K component would be plus 0.8253 FCD K. And our units on this should be newtons. Let me move that K down so it's not hitting the picture. Well, that's my final vector in here. From there, I can say, well, what point should I sum moments about? Really, I could choose anything in here. I would choose something where I have forces at least. So I'd probably do A, B, C, or D in there. It really doesn't matter which one. I'm going to choose point B. But that's going to give me my second step. I need to get each moment arm vector. Express each moment arm. Each moment arm as a Cartesian vector. As a Cartesian vector. And for me to do this, I have to pick a point I'm summing moments about. So I'm going to come in and, for my example, I'm going to choose point B. So I'm going to document that. I am summing my moments about point B. This will give me moment vectors, and I'll eventually get this all equal to 0. But if I'm summing moments about point B, I need moment arm vectors that go from B to every single force in here. So I'm going to need, what's my R, my position vector, that goes from B to A. If I'm going from B to A, let's loosely sketch this in. Can I do this without it getting too crowded? A little bit. From B to A would be this line right here. B to A. I would need a B to D, coming down kind of like this. A B to G. A handful of vectors that I'm filling in as we go in and do that. RBA, A is the tip of that arrow, B is the tail. So I want the coordinates of A minus the coordinates of B. Always tip minus tail. This is going to get me 1.2I plus 0J plus 0K meters. My position vector that goes from B to B, that's going to be 0. There's no change in my coordinates in here. RBB isn't a thing. I just leave it off, which kind of makes sense. I'm not causing moment about point B because my BX, BY, BZ all pass through point B. If my force passes through the point I'm taking moment about, it shouldn't cause any moment. So we can just leave that one off. But I will need an RBG. RBG. My position vector that goes from B to the weight. If we do tip minus tail here, this is going to get me the coordinates of the weight minus the coordinates of B. And this works out to be 0.6I plus 0.5J. And my K component is 0. Plus 0K newtons. And then I have one last that I need. I need to get a position vector from B to my force, which I get two choices in here. My force I know passes through C and through D. I could do RBD or I could do RBC. Either way will get me the same final answer. When I put it into the cross product, it will take care of the math on that for us. Either one of those position vectors. Even though they're going to be different position vectors, the math will balance out and we get to the exact same final answer in here. So just choose one of them. RBD is what I'm going to work with. So now I'm doing the coordinates of D minus the coordinates of B. That's going to get me 1.6I. 1.6I. Plus 0.65J. And I'm on the XY plane for both. So plus 0K. And again, we are in, not newtons that I wrote down up above. That'd be a force vector. We're in meters. Meters. That is my second step in here. From here, we can come in and say, well, let's start making my cross product. I know as I tackle all of this, my sum of my forces and my sum of my moments has to get us to 0. I have a whole bunch of force vectors that I wrote out here. I could sum X, Y, Z components for this. Or I could come in and get my moments set up. So let's do the moments. I'm actually going to make my equation for this. the sum of my moments about point B is going to get us to. And I'm going to need 3 cross product matrices in here. One for each force. We're not going to count B because it causes no moment. So let's get that up and going. So I'm going to use, in my first one, let's do RBA. We'll write down what I'm doing. RBA. That's my force vector, or my position vector. I need to cross that with a force vector. That force vector should be A. So we can come in and just fill in those pieces. RBA, I know is 1.2, or my top is I, J, K. RBA is 1.2, 0, 0. And my A vector is 0, AY, AZ. 0, AY, AZ. We can add into that another cross product. Plus, again, my top is still just I, J, and K. This time, let's work with the RBG. So I need to pull in the weight. So this would be RBG. And the weight that I'm pulling in on this one. RBG, I know is 0.6, 0.5, 0. 0.6, 0.5, 0. And the weight I found up above is 0, 0, negative 245.3. Negative 245.3. But that leaves us with just one last cross product that I need to fill in here. So I'll add in one more thing. Plus, if I make my matrix again, I'm going to have the top is I, J, K. This one takes a little bit more room to write, so hopefully that's enough. But really, what I'm filling in here is my very last thing. I need an RBD, RBD. And I'm crossing that with FCD, FCD. So it's my RBD vector in here. RBD, I know, is 1.6.65. 1.6.65, 0. And FCD is the one that takes up room. My I is 0 on this. My J is 0.5647. 0.5647. I'm going to put the FCD down below. FCD. And the K is 0.8253. 0.8253 FCD. But all of this, as I set that up, has to get me to 0. So I can start coming in and making my cross product matrices then. We can come down below and really say this is summing our moments up about point B. Should get me to, in my first matrix, if I look at the I, it'd be 1.2, or we ignore I, so it'd be the J and K. We're looking at these two. Top left times bottom right. 0 AZ minus 0 AY would just be 0 I, my I times 0. Then we always subtract out J, so minus J, which is what makes the math work out right. And I look at the I and K, so top left 1.2 times bottom right AZ, 1.2 AZ, minus the top right times bottom left. Minus 0 times 0 is 0. So we'll just leave it as is. Then we look at the K piece. We go back to adding plus K times, we have the I and J terms left here. So the top left would be 1.2 times the bottom right AY. 1.2 AY. Minus the top right times bottom left. 0 times 0 is 0. That's our resultant of this first matrix. We still have unknowns in here. That's okay. We'll eventually get to applying equilibrium in this. But let's come in and to go to the next one. We'll just keep writing this out. Plus, we look at our I component here. We'd have 0.5 times negative 2, 45.3. 0.5 times negative 245.3 times our top right times bottom left, 0 times 0. That's it for us. Go to the j component, we subtract j, and we would have, we're looking at the I and k, 0.6 times negative 245.3. 0.6 times negative 245.3 minus top right 0 times bottom left 0. And then getting our last piece in here for our k, we look at our I and j. We go back to adding plus k times top left 0.6 times bottom right is 0 minus 0.5 times 0. So this is just k times 0. Let's go, I don't think I'm going to have room here. So let's go to the next line to finish this up. So we'll go one more time. We need to add in an I component for my final matrix in here. I'm looking at the j and k. So 0.65 I times 0.65 times 0.8253 FCD. Top left times bottom right. 0.8253 FCD. Minus our top right times bottom left. 0 times anything is 0, so we'll just leave it there. But then we'll go to our subtraction. Minus j times, we look at the I and k. Top left times bottom right is 1.6. The top left times our bottom right, 0.8253 FCD. FCD. Minus our top right, 0 times our bottom left, 0. We can just leave it there. And our very last piece then, we can come in and say, we go back to adding plus k times, we look at the I and j pieces. So k times, top left is 1.6 times our bottom right, 0.5647, 0.5647 FCD. Minus our top right, 0.65 times bottom left, 0 is just 0. This is a large, nasty looking equation. If we can set this entire thing equal to 0. When we actually start applying equilibrium, we'd really just be saying, well, let's take all of our I terms. 0 plus 0.5 times negative 245.3 plus 0.65 times 0.8253 FCD equals 0. Right there, I only had one unknown, FCD, in the I components. I can solve for I. I'm going to pause this video, though. I'm going to erase and kind of condense down to just this line and my force vectors and kind of get them back up at the top so we can do the algebra and solve everything out. So we'll be back in just a second to finish up this problem. All right, well, welcome back. I basically just came in and erased a ton of the work, getting us to just what are our force vectors, what's our one giant moment vector that we made. And we know that's equal to 0 when we sum everything up. From here, we really are ready to just come in and do our next step is apply equilibrium into this. So what I come in and try to do is say, what's one equation I can make if possible and find one unknown out for everything. This is a lot harder in 3D than it is in 2D because there's 6 possible equations for us. But if we look at everything, in our forces, I'd have no I, no I, no I. Really, there's just one I component. We can start there. It'd be a pretty easy equation for us. If I go to my J's, I'd have a J component, no J component, I'd have a J component. I'd have K, 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 K. There's a bunch of K components I could work with. Really, in terms of forces, all I could really do is sum forces in the X. I only have one force there. Maybe an easy one. We'll save that for later, though. If I go to moments, in my I components, I have no I. I'd have a constant here and one unknown in there. So if I sum up all my I components, I get an unknown. So let's write that as the sum of our moments about point B, and we're looking at just the I components for this, is going to get us nothing, so we'll leave it off. 0.5 times negative 245.3, 0.5 times negative 245.3 plus 0.65 plus 0.65 times 0.8253 FCD. And that's all of my I components. I can set that entire thing equal to 0, which gives me enough. I can solve this for FCD. My force in that thin link CD is 228.6 newtons. 228.6 newtons, which is my first of our 6 answers for everything. From there, if I go and start counting my unknowns, this one doesn't count anymore because I know it. So if I go to my J, I'd have AY, I'd have a known constant here, and my third one, FCD is now known, so I'd really only have AY or AZ as an unknown here. So let's try summing my moments about point B, and I'm just grabbing those J components. So let's come in here. I have negative 1.2 AZ, negative 1.2 AZ. Don't forget we have a negative J. We need to pull in the sign from the outside on this. Minus 0.6 times negative 245.3. And then continuing that on, we get to minus 1.6 times 0.8253 FCD, 228.6. FCD, 228.6. That's my last J term for the moment. I can set that equal to 0, which will get me my AZ. AZ is negative 128.9. Negative 128.9. We dealt with 2D, and that's in newtons. When we dealt with 2D, I always tell us to get our answer report as a positive and show the correct direction. In 3D, I'm not going to worry about that. It becomes so convoluted because we have to alter previous equations if we set this up assuming it was negative. It's just not worth it. Just report it as is. I typically then come in and assume my forces in the positive directions to kind of pair in with that. But there's other ways we could do that. Finally, let's come in for our moments. I can get my K components. 0, something in terms of FCD, and an AY in here. So let's sum up our moments about point B. And I'm just grabbing those K terms for everything this time around. This is 1.2 AY. Taking the K term, plus 0, so I can leave that one off, plus my very last one I wrote down here, 1.6 times 0.5647, 0.5647 times FCD, which we still know is 228.6. 228.6, and that's going to get us to 0. That gives me enough that I can find AY. It's my only unknown in this equation. If I solve for AY, I'm going to get AY equals a negative 172.1. Negative 172.1 newtons. Which is my third answer for this. I still have 3 unknowns, but I can still sum forces in 3 directions. I have 3 equilibrium equations to go. I should be able to find all of them. So let's just do X first. If I sum up my forces in the X direction, I have in A, I have 0. In B, I have a BX. I'm looking at the I components. So BX, from the weight, there's nothing. From FCD, there's nothing. So it's only BX. I can set that equal to 0. And that's another one of my answers. I could have done that one earlier. It wouldn't have changed anything we've done, though. From here, let's go ahead and sum forces in the Y direction. Summing our forces in the Y. I have, from A, I have an AY, but I found AY. It's negative 172.1. Negative 172.1. I'm going to even document that because this gets hard to remember where numbers came from. That's AY for us. In my next vector, I have a BY. I haven't found BY yet, so let's put that in as an unknown. plus by. And I don't have a y component of the weight, but I do for FCD. So I'll need to add in FCD's component. Plus 0.5647. 0.5647. I'm up here looking at FCD. 5647 times FCD, which we found was 228.6. Again, this piece is FCD. But that's everything for us. That's all of my J terms. So I can set this equal to 0. AY is my only unknown. Or BY, sorry, we solved for AY. BY is my only unknown. I'm going to get that BY is 43.0 newtons. Which leaves me with just BZ as an unknown left to go. I can sum forces in the Z direction and get that one. Summing forces in the Z direction. Now I'm taking my K components. So I have AZ, we found this one earlier, 128.9, negative 128.9. Again, let's document that one. That is my AZ. For my next one, I do have a BZ. I am trying to find that one. So plus BZ. Going to my weight. I do have a weight, but it's all known. So just minus 245.3. I'm going to document that. That is the weight term of all of our work. And then FCD, plus 0.8253 FCD, plus 0.8253 FCD, I know is 228.6. 228.6, that was again FCD. But this all has to get us to 0. That's all of our K components from our force vectors. If our entire forces add to 0, then all of our I components, all of our J components, all of our K components have to also be 0. I can solve for BZ, and I'm going to get here that BZ is equal to 185.5 newtons, which is my final answer for that. Our 3D problems, they can take away ways to get through in here. Go slow and steady with them. You can get through this. It's totally a doable thing. We just need to be meticulous in how we're setting everything up in here. And it's really annoying because these are easy to make, a simple sign error on somewhere, and it's going to be awful to try to track that one down. Slow and steady is the key to these ones. You can do these. But hopefully this is a useful thing for you. If it was, stick around, watch more videos. Let's get you an A with JJ.